In this lesson, we're going to talk about thermostats, one of the basic control devices of most HVAC circuits. Your typical wiring diagram looks like this. Over on the right-hand side, you'll see a label indoor unit, and thermostat is right above it. The thermostat has many functions. It can signal heat, it can signal cool, it can deal with indoor blower fans, it can deal with compressors and condensers. Remember, there are two types of circuits. The control system are series and a load. Loads are normally wired in parallel. Air conditioning has several levels of controls. There are the basics and then the more complex system. So do the controls. These levels are split into basic on-off control, safety controls, and efficiency or comfort controls. Thermostats are the most basic control device for the air conditioning system. This is where it all starts. Customer turns it down, AC should come on, or customer turns it up, heat should come on. In most split systems where the air handler is inside and the condenser is outside, it's connected by refrigerant piping and the thermostat wiring, which is 24 volts. The thermostat is the most frequently changing device in the HVAC industry, but they all do the same thing: turn it on and turn it off at the proper temperature. Basic function of the thermostat is to respond to a change in temperature by opening or closing a set of contacts. A thermostat is a switching device. Thermostats can be line voltage, control voltage, or direct digital. Line voltage are the most often used in heat applications that are electric as well as in refrigeration. Control voltage thermostats are mainly used in residential or small office applications. Direct digital controls, DDC systems, are most often used in large office, commercial, or public buildings. For the purpose of this term, we will be discussing control voltage, low voltage thermostats. There are now three types of sensing elements that are used in thermostats. First, the sensing element is a controlling part of the thermostat that moves or causes the contacts to close when the temperature senses a change in temperature. Bimetal contains two pieces of dissimilar metal that are welded together. These metals expand and contract at a different rate, and when heated or cooled, they bend and move the contacts closer together or further apart. These are examples of bimetal. The top one will move up and down. The U-shaped one will also move up and down. The one that's a spiral will work in a circle. The movement of the metal and the contacts can either move a mercury bulb or bring magnetic on the contacts together. The thermostat must have a way of making a good connection with the contacts. This is called snap acting. The remote bulb thermostat has a bulb filled with a liquid or gas. The liquid and gas expands, travels down a capillary tube, and this expanding material puts pressure onto a diaphragm. This in turn closes or opens a set of contacts. The solid-state thermostat is a digital or programmable thermostat. It uses solid-state control, no moving parts. Uses a material that changes resistance based on temperature. Knowing the resistance, the thermostat can judge and display the correct temperature. They have longer and more accurate lifespan, and they don't have moving parts. When a furnace call is warming up after the thermostat calls for heat, the temperature continues to drop. The furnace holds a lot of heat and will continue to provide heat to the space as it cools down. This is called overshoot. To prevent this, most thermostats contain a device called a heat anticipator. Heat anticipators are small resistors built into the thermostat that generate some heat during a call for heat. The bimetal senses this additional heat and causes the thermostat to shut down a little before the room is satisfied. This allows the remaining heat in the furnace or water to be released into the room while preventing the room from overheating. Solid-state thermostats don't have adjustable anticipators. They don't need them. The computer control can do this on its own. Adjustable anticipators must be set to the amperage of the gas valve or the heating relay. This is an example of a heat anticipator that's in series with the contacts. So if the contacts are closed, the anticipator is energized. Contacts are open, the anticipator is not energized and not providing heat. There's some problems with heat anticipators. If the setting's too low, you have excessive anticipations. The on cycles are too short. It's going to be rapid cycling, and there's going to be a tendency for the temperature of the building to stay a little bit below the settings. If the anticipator setting is too high, you're going to have insufficient anticipation. On cycles are too low, infrequent cycling, and you're going to have very wide temperature swings. Cooling anticipators are not found that often, but occasionally you'll see them on some commercial thermostats. They're the same as the heating anticipator, but they provide power during the off cycle. It reduces the time it takes for the contacts to make contact on a rise in room temperature. They are not adjustable, but manufacturers set for a specific design. A cooling anticipator is in parallel with the contacts. So when the contacts close, the current goes through the path of least resistance and bypasses the cooling anticipator. If the resistor is too small, you're going to have short off times, short on times, and rapid cycling. Temperature maintained closer to setting with a tendency to go a little bit above. If the resistor is too large, the off time is too long, on times are too long, fewer cycles, and you're going to have wide temperature swings with a tendency to lag. So looking at this chart, if we have 72 degrees as the set point, and with anticipation the temperature of the bimetal is 74 degrees, okay, then you'll see that the only one that makes sense, the one that's the closest to the set point, is line 4. Cycles, but doesn't go too far above, doesn't go too far below. When you're dealing with thermostats, know what voltage is controlled. Do not touch a broken mercury thermostat. It is environmental waste and can burn you severely. Make sure you dispose of any mercury thermostats in appropriate designated spaces. No matter what thermostat, the basic principle in the wiring is the same. You have a G terminal, an R terminal, a Y terminal, and a W. R is your power into your thermostat. G controls your blower fan or your indoor fan. Y is your cooling, and W is your heating. You might have some additional terminals. C for common, it's the other side of the transformer. O might be a reversing valve for heat pumps. Y2 might be second stage cooling, and W2 might be second stage heating. Thermostats may have different wiring diagrams like the one I'm going to show you next, but the functions are still the same. The easiest way to find out what the terminals on a thermostat do is to look at the manufacturer's direction. This is an example of a 2 cool, 2 heat. Notice the different types. Notice the different designations of the thermostat terminals. They still do the same thing. They just have different letters on them. You might have to look it up. You might have to call the manufacturer. This is an example of a control connection. Again, designations may be different, but they still do the same thing. You still have R, G, W, and Y. More and more with electronic thermostats, you're going to see thermostat blocks. The interface connects to the HVAC system. You have an electronic control. You have a display, user, and temperature measurement. Those are the inputs. Once a call for cool has occurred, the next step is to control the condenser. Before turning on the compressor, the system has to make sure it's protected. Like low pressure, high pressure. Did all the refrigerant work out, or is the system still safe under the pressure limits? Has enough time elapsed since the last run? Has enough time elapsed to let the system pressures equalize? Has the compressor locked out on the last run? Is it warm enough to run the unit? These are all safety controls. Time delay relays are used to provide a period of time between a control change and the next control change. For example, we want to make sure that there's 5-minute delay between compressor runs. We have a choice of 2 time delay relays. We have a thermal time delay relay, which can provide either a make on break or a break or a delay on break. Delay on make. Relay will delay following a thermostat call. It's wired in series with the thermostat and the control device. Heater inside the relay heats up for a certain amount of time and then closes the circuit. This is an example of the delay on make. Notice the thermostat goes to the time delay relay, and then the time delay relay goes to the contactor. Delay on break is wired in parallel with the control device. When the call for cooling ends, it will heat a heater up and prevent the device from turning back on for a certain amount of time. The delay on break is wired in parallel. Notice again, the thermostat goes to the time delay relay. The time delay relay actually goes back to common and the contactor common. This is the delay on break.